Before you drift fully into rest, take a moment to settle yourself. Lie down, close your eyes, and feel the weight of your body pressing gently against the surface beneath you. Let the quiet of this moment surround you, a calm invitation to explore the slow, deliberate rhythms of the natural world. Have you ever wondered what would happen if one of the planet's most vital systems quietly, imperceptibly began to falter? The Atlantic Meridional Overturning Circulation, or AMOC, is an immense global ocean current, transporting warm tropical waters northward along the surface of the Atlantic and returning colder, denser waters southward at depth. This circulation is the heartbeat of Earth's climate system, carrying heat and salt in a precise balance that sustains regional temperatures, influences rainfall patterns, and regulates the transfer of carbon between ocean and atmosphere. Its power is invisible to the casual observer, yet its presence shapes the lives of millions, particularly across Europe, where winter temperatures are softened by the steady northward flow of warmth. The AMOC operates on a principle of density and thermohaline motion. Warm water from the equatorial Atlantic is less dense, carrying heat toward the north, where it cools as it approaches higher latitudes. In the North Atlantic, the water becomes colder and more saline, growing denser until it sinks, plunging into the deep ocean to begin its return journey toward the south. This continuous loop, often referred to as the global conveyor belt, takes centuries to complete a full cycle, yet its effects manifest daily in the weather, ocean temperatures, and marine ecosystems. Salinity and temperature are intimately linked in this system. Any significant influx of fresh water from melting ice sheets or increased precipitation can disrupt the density gradient that drives sinking, potentially slowing or halting the circulation. Historical records, ice cores, and sediment deposits indicate that the AMOC has experienced variations and abrupt changes in the past. During the last glacial period, shifts in ocean circulation corresponded with sudden cooling events in the northern hemisphere, known as Heinrich events. Layers of ice-rafted debris preserved in the North Atlantic tell a story of massive iceberg discharges, freshwater influx, and the resulting collapse or slowing of the current. Paleoclimate studies revealed that such interruptions could lower average European temperatures by several degrees Celsius, drastically altering ecosystems and human settlements even millennia ago. These ancient signals serve as both a warning and a guide to understanding the sensitivity of the system today. In modern times, scientists track the AMOC using a combination of satellite altimetry, Argo floats, and deep ocean moorings. Continuous measurements over the past decades suggest a gradual weakening, correlated with rapid ice melt in Greenland and increasing precipitation in the North Atlantic. The precise mechanisms involve complex interactions between surface warming, freshwater input, and changes in wind patterns. Models indicate that as the North Atlantic freshens, the density difference required for deep water formation diminishes, slowing the current. The prospect of a significant reduction or even a complete halt raises questions about the regional and global climate implications, particularly for Europe, which depends on the northward heat transport to maintain milder winters than would otherwise occur at its latitude. The influence of the AMOC on Europe is profound. Cities from Lisbon to Oslo owe part of their temperate climates to the warm waters delivered by the Gulf Stream and its extension into the North Atlantic. The moderation of winter temperatures allows vegetation to survive at higher latitudes, supports agriculture with predictable seasonal cycles, and stabilizes atmospheric pressure systems that dictate rainfall distribution. A slowing of the current could amplify seasonal extremes, intensifying cold spells, altering precipitation patterns, and increasing storm frequency and intensity. Coastal regions would face changes in sea level rise due to the redistribution of water masses, while northern ecosystems would experience shifts in species composition, productivity, and migration patterns. The link between Greenland ice melt and AMOC disruption is particularly critical. As large volumes of fresh water enter the North Atlantic, the salinity drops, reducing the water's density. In laboratory and modeling studies, even small changes in salinity can lead to measurable reductions in overturning strength. Paleoclimate evidence suggests that during periods of accelerated ice melt, the AMOC slowed dramatically, leading to abrupt cooling events over Europe and parts of North America. The feedback loops are complex. A slower AMOC reduces heat transport, leading to regional cooling that can temporarily stabilize ice sheets, but over longer periods, the altered currents can contribute to sea level rise, disrupt monsoons, and affect the carbon balance in oceans. Ocean currents are intimately tied to the carbon cycle. Deep waters formed in the North Atlantic carry dissolved carbon from surface waters into the ocean interior, where it can remain sequestered for centuries. A slowdown in the AMOC would reduce this transport, leaving more carbon in the atmosphere and potentially accelerating warming elsewhere, even as Europe experiences colder conditions. This paradox highlights the non-linear responses of Earth systems. A localized cooling event may coincide with a broader acceleration of global warming, underscoring the interconnectedness of climate processes. Observational networks reveal that the AMOC has weakened by roughly 15% over the past century, a rate unprecedented in at least the last millennium. Satellite gravity measurements show increasing mass loss from the Greenland ice sheet, while ocean float arrays indicate slowing transport of warm surface waters northward. Coupled climate models simulate scenarios in which continued ice melt and freshwater input could bring the AMOC close to a tipping point within the next century, though uncertainty remains about the exact timing and magnitude. Even a partial reduction would have cascading effects, from temperature and precipitation shifts to changes in hurricane intensity and shifts in tropical and mid-latitude ecosystems. Europe's vulnerability to these changes varies regionally. Northern Europe would experience harsher winters, with temperatures dropping below historical averages. Southern Europe might face drier conditions as the alteration in atmospheric circulation reduces precipitation. The Mediterranean basin, already susceptible to drought, could experience further water stress. Agriculture, from cereal production to vineyards, would need to adapt to altered growing seasons and increased variability. Urban infrastructure, designed for historical climate patterns, might confront new challenges in energy demand, transportation, and flood management. The implications extend beyond human societies, influencing forests, wetlands, and coastal ecosystems, which respond slowly but persistently to climatic shifts. The broader climate system does not operate in isolation. Changes in the North Atlantic circulation influence tropical rainfall, monsoon intensity, and even the Southern Ocean's capacity to absorb carbon. The interconnections are mediated through atmospheric teleconnections, where shifts in temperature and pressure patterns ripple across continents. A slowdown of the AMOC could disrupt the timing and intensity of the West African and South Asian monsoons, altering the livelihoods of millions who rely on predictable seasonal rains. In the Southern Hemisphere, the distribution of heat and salinity affects Antarctic ice shelves and deep water formation, creating potential feedbacks that propagate back to the North Atlantic, reinforcing or dampening the initial slowdown. Freshwater entering the North Atlantic from Greenland and Arctic ice melt is only one piece of a larger puzzle. The ocean surface, warmed by solar radiation and modulated by seasonal winds, interacts with the atmosphere in a continuous exchange of heat, momentum, and moisture. When surface waters lose density through the addition of fresh water, their ability to sink diminishes, weakening the overturning circulation. This slowing does not happen uniformly. Localized patches of reduced sinking can propagate instability along the current's path, altering temperature and salinity gradients in adjacent regions. Researchers studying these gradients find subtle shifts in thermocline depth, variations in salinity profiles, and anomalies in sea surface temperature that signal early stages of circulation disruption. Each year, the measurements accumulate into a detailed narrative of change, revealing that the ocean is responding incrementally to forces both natural and anthropogenic. In the North Atlantic, the decline in overturning strength translates directly into the distribution of heat across Europe, Scandinavia, and the British Isles, which owe their relatively temperate winters to the northward transport of warm water, could experience extended periods of lower temperatures. Mean winter temperatures might drop several degrees Celsius over decades, enough to influence snow cover, river freeze-thaw cycles, and the timing of spring melt. In southern Europe, shifts in atmospheric circulation induced by altered ocean heat fluxes could reduce winter precipitation, stressing water resources and modifying growing seasons. Historical records of the Little Ice Age offer analogues, showing that even modest reductions in oceanic heat transport can produce widespread cooling, while paleoceanographic studies reinforce the sensitivity of these regions to changes in the AMOC's vigor. The ecosystem response to a slower AMOC would be equally nuanced. Marine species rely on the current to distribute nutrients and oxygen, maintaining productivity in both coastal and open ocean environments. Plankton communities, forming the base of the marine food web, are sensitive to changes in water temperature and nutrient upwelling. A weakened circulation may alter the timing and location of phytoplankton blooms, cascading through the food web to fish, seabirds, and marine mammals. Forests in northern Europe would confront shifts in frost patterns and soil moisture, while wetlands and peatlands may experience longer periods of freezing or desiccation, affecting carbon storage and ecosystem function. Each ecological change is interconnected, a quiet ripple moving outward from a single, measurable alteration in the ocean's flow. Sea level changes associated with AMOC slowdown are subtle yet persistent. A redistribution of water mass across the Atlantic can raise or lower local sea levels by tens of centimeters, depending on region and depth. In Europe, coastal cities and low-lying agricultural areas would need to contend with modified tidal patterns and increased risk of storm surge. These physical changes interact with human systems, from port infrastructure to flood management practices, requiring adaptation to conditions that differ from historical norms. Beyond Europe, tropical regions may experience enhanced sea level rise along the US eastern seaboard and parts of West Africa, illustrating the far-reaching consequences of shifts in North Atlantic circulation. Freshwater inputs and surface warming do not act in isolation. Wind patterns over the North Atlantic influence the upwelling of deep waters and the distribution of surface heat. Changes in the polar jet stream, linked to Arctic amplification, further interact with ocean circulation, modifying weather patterns across the Northern Hemisphere. Models suggest that even modest alterations in these combined forces can amplify temperature extremes, alter storm tracks, and produce persistent anomalies in precipitation. The atmosphere and ocean respond together in a complex dance, each influencing the other across scales of days to decades, creating conditions that are predictable in broad terms but inherently variable in detail. Carbon cycling in the ocean remains a critical component of understanding the consequences of AMOC disruption. Deepwater formation carries dissolved carbon into the ocean interior, temporarily sequestering it from the atmosphere. A slowdown in overturning reduces this transport, leaving more carbon at the surface where it can contribute to warming. Ocean acidification, already underway due to anthropogenic emissions, may accelerate in regions of reduced circulation, affecting calcifying organisms and altering marine food webs. The interplay between circulation, carbon storage, and chemical composition of seawater illustrates how a single physical change can ripple through chemical, biological, and climatic systems, producing effects that extend far beyond the North Atlantic. Modern monitoring networks provide a continuous window into these dynamics. Arrays of moored instruments, drifting Argo floats, and satellite altimetry work together to measure temperature, salinity, and flow velocity at multiple depths. Time series from these observations reveal year-to-year variability, as well as long-term trends, allowing scientists to detect weakening signals before dramatic consequences manifest. Combining these measurements with coupled climate models, researchers can simulate future scenarios, estimating potential outcomes under different greenhouse gas emission pathways. While uncertainty remains in exact timing, the convergence of multiple independent datasets paints a clear picture. The AMOC is sensitive, responsive, and at risk of further weakening if current trends persist. Beyond physical and ecological effects, human societies are intertwined with these shifts. Energy demands in Northern Europe may rise as colder winters increase heating requirements. Agriculture faces adaptation pressures, from altered planting schedules to crop choice modifications. Water resource management in Southern Europe may become more complex, with reservoirs and irrigation systems needing to account for modified precipitation patterns. Coastal urban planning must consider changes in tidal regimes and storm surge potential, while insurance, infrastructure, and emergency services adjust to new risk profiles. The cumulative effect is a subtle yet pervasive influence on daily life, underpinned by changes in ocean circulation that are invisible to the naked eye, yet powerful in consequence. The AMOC's influence extends globally through a network of atmospheric teleconnections. Changes in North Atlantic heat transport affect tropical rainfall patterns, shifting the timing and intensity of monsoons in Africa and South Asia. Southern Hemisphere currents and Antarctic ice dynamics respond to alterations in northern circulation, feeding back into global climate patterns. These feedback loops operate over decades to centuries, revealing the interconnected nature of Earth's climate system. Each adjustment, no matter how small, propagates through oceans, atmosphere, and biosphere, reminding us that the slow movement of water beneath the surface governs more than the immediate temperature of distant seas. As the observations accumulate and models evolve, a clearer picture emerges of thresholds and tipping points. While complete collapse of the AMOC remains unlikely in the near term, even partial reductions in strength produce measurable climatic shifts. Research highlights that once freshwater input surpasses certain limits, the system may respond abruptly, producing rapid cooling events that echo patterns observed in the geological record. These potential changes are neither uniform nor instantaneous. They manifest as gradual shifts in temperature, precipitation, and circulation patterns, yet their cumulative effect can be transformative over decades. Understanding these thresholds is critical, informing both scientific inquiry and public policy, guiding efforts to mitigate risk and adapt to changing conditions. Europe's landscapes, both natural and cultivated, are finely attuned to the current climate, and even modest shifts in ocean circulation could have lasting consequences. Northern forests, composed of conifers and mixed species, respond to winter temperatures, soil moisture, and the timing of snowmelt. A reduction in northward heat transport would lengthen frost periods, slow the onset of spring growth, and alter the decomposition rates of organic material in soils, subtly changing nutrient availability. Wetlands and peatlands, significant carbon reservoirs, are sensitive to both temperature and hydrological cycles. Extended freezing or altered water levels could suppress microbial activity temporarily, but the longer-term impact may be the release of stored carbon, creating a feedback loop that slightly accelerates regional warming, even amid cooler surface temperatures. Such shifts would be gradual yet continuous, the quiet movement of change imperceptible until seasonal patterns begin to diverge noticeably from historical averages. Agricultural systems would likewise confront incremental adjustments. Cereals, root crops, and fruiting plants rely on the predictability of frost dates and precipitation timing. Even small deviations from expected conditions can influence germination success, flowering, and harvest yields. Farmers might face altered planting windows, needing to consider the possibility of late cold snaps or irregular rainfall. Vineyards, particularly in France, Germany, and northern Italy, could experience delayed ripening or reduced sugar accumulation in grapes, directly impacting both production and quality. These subtle, often cumulative effects demonstrate how a distant ocean current exerts influence over terrestrial ecosystems and human activity, threading through the food web and extending into the economy without visible fanfare. Coastal regions, too, would feel the effects of shifts in the AMOC. As the northward movement of warm water slows, the distribution of ocean mass changes, influencing local sea levels along the European seaboard. Ports, estuaries, and low-lying agricultural areas would contend with altered tidal ranges and an increased likelihood of storm surge penetration during winter storms. Infrastructure designed for historical sea levels may require reinforcement, adaptation, or relocation over the long term. Beyond the built environment, marine habitats such as estuaries and and tidal flats face stress from both rising waters and changes in salinity, affecting breeding grounds for fish, migratory birds, and other species that rely on these transitional ecosystems. These cumulative, gradual transformations are emblematic of the interconnectedness of ocean circulation and life along its margins. The human response to these changes is similarly gradual, yet deliberate. Energy demand in Northern Europe may rise during colder winters, increasing pressure on heating systems and electricity grids. Water resource management in Southern and Central Europe could confront new challenges as river flows and precipitation patterns deviate from long-term averages. Urban planners, agricultural managers, and policymakers must interpret the signals from oceanographic and atmospheric monitoring to inform decisions that mitigate risk and maintain resilience. Although the adjustments required may be incremental, the feedback between human activity and climate shifts underscores the complexity of the system. A weakening AMOC modifies conditions on land, which in turn influences energy use, agricultural practices, and urban infrastructure, creating interwoven cycles of adaptation and response. Marine ecosystems are particularly sensitive to the changes in circulation. The northward flow of warm water carries nutrients and oxygen that sustain high productivity along the European continental shelf. A slower current reduces the upwelling of nutrient-rich deep waters, influencing the timing and location of phytoplankton blooms, which form the foundation of the marine food web. Fish populations, from herring to cod, may shift their ranges in response to altered temperatures, impacting fisheries that support local economies. Seabirds and marine mammals, dependent on predictable prey. Availability must adjust migration patterns, breeding cycles, or foraging strategies, highlighting the cascading biological consequences of physical changes in ocean circulation. Each adjustment may seem subtle at the scale of weeks or months, but compounds over years to restructure the composition of marine ecosystems. The interconnection between ocean currents and atmospheric circulation patterns becomes apparent when considering storm frequency and intensity. The northward transport of heat by the AMOC influences the positioning of the jet stream, affecting both the trajectory and strength of mid-latitude storms. A weakened current may allow the jet stream to meander more, creating prolonged weather patterns that manifest as colder winters or wetter, stormier periods in some regions, and drier conditions in others. These patterns, in turn, influence soil moisture, river flow, and sediment transport, demonstrating how an unseen shift in the depths of the ocean propagates through atmosphere and land to affect the rhythms of daily life. The subtle coupling of ocean and atmosphere operates over years and decades, often imperceptibly, yet it underpins the stability of the climate system upon which human societies have long depended. The historical record provides perspective on these potential transformations. During the Younger Dryas, approximately 12,000 years ago, abrupt cooling occurred in the Northern Hemisphere following disruptions in ocean circulation due to meltwater influx from retreating ice sheets. Average temperatures in Europe dropped significantly over a matter of decades, while ecosystems and human populations adapted to the colder, drier conditions. Ice core and sediment analyses reveal rapid changes in salinity and temperature across the North Atlantic, reinforcing the sensitivity of the overturning circulation to freshwater inputs. These events illustrate that even temporary interruptions in the AMOC can have pronounced effects on regional climates and emphasize the importance of monitoring contemporary trends to anticipate potential outcomes. Observations and models converge on the understanding that the AMOC is currently in a weakened state. Long-term measurements reveal reductions in deep water formation, diminished northward heat transport, and subtle shifts in sea surface temperature and salinity profiles. Climate simulations suggest that continued warming and ice melt could further reduce circulation strength, with effects manifesting over decades rather than centuries. This combination of evidence highlights the necessity of integrating observations across multiple temporal and spatial scales, from the minute variations detected by oceanographic instruments to the broad climate responses projected by sophisticated models. The continuous dialogue between data and modeling illuminates the dynamics of the system, allowing scientists to anticipate consequences even amidst uncertainty. Globally, the influence of a weakening AMOC extends beyond Europe. Tropical rainfall patterns, particularly monsoons in West Africa and South Asia, are modulated by heat distribution across the oceans. Variations in North Atlantic circulation alter pressure systems and sea surface temperatures, which in turn shift the timing and intensity of rainfall thousands of kilometers away. In the southern hemisphere, Antarctic ice shelves and the Southern Ocean respond to altered heat and salinity distributions, with feedback effects that can propagate back to the North Atlantic. The ocean's conveyor belt thus functions as a planetary integrator, linking distant regions in a network of energy, heat, and moisture transfer. Each adjustment resonates through the global system, reminding us that no oceanic process is isolated. The potential for tipping points within the AMOC system underscores the delicate balance of oceanic circulation. Scientific models suggest that as freshwater input from Greenland continues to increase, the North Atlantic could approach thresholds where deep water formation ceases in localized regions. Even partial cessation produces cascading effects, altering the vertical structure of the ocean and modifying temperature and salinity gradients along the path of the current. These changes propagate slowly, yet inexorably, influencing atmospheric patterns, ocean heat storage, and the distribution of nutrients critical for marine life. Monitoring such thresholds requires continuous observation, combining direct measurements of water movement with remote sensing and climate modeling to detect subtle, early signals of systemic stress. In practical terms, a weakened AMOC would reshape European seasonal patterns over decades. Winters in northern regions would lengthen, bringing extended periods of snow cover and lower mean temperatures, while spring thaw could be delayed, affecting rivers, lakes, and the timing of agricultural activity. Southern Europe might experience altered rainfall regimes, with some regions becoming drier due to shifts in the jet stream and associated pressure systems. These changes would ripple through ecosystems. Plant phenology may shift. Insect life cycles could desynchronize with flowering and crop growth, and migratory species may adjust routes and timing in response to altered climate cues. Each of these adjustments, while individually modest, aggregates into a broader transformation of ecological and human landscapes. The interplay between AMOC-driven ocean currents and carbon storage in the deep Atlantic is another key aspect of the system's sensitivity. Deep water formation serves as a conduit for sequestering carbon from the surface, drawing down atmospheric carbon dioxide over centennial timescales. A slowdown in circulation reduces the efficiency of this sequestration, leaving more carbon in the upper ocean and atmosphere. The combination of reduced sequestration and ongoing emissions may accelerate warming in other regions, even as Northern Europe experiences colder conditions. This divergence illustrates the non-uniform nature of climate responses, where a single physical alteration can simultaneously cool some areas while warming others, highlighting the complexity of Earth system interactions. Marine ecosystems reflect the physical changes in ocean circulation with subtle yet persistent adjustments. Species distribution shifts as temperature and nutrient availability evolve, while primary productivity in the North Atlantic may decline in areas previously enriched by upwelling. Fish populations respond to these shifts by moving to regions with optimal conditions, influencing fisheries and food security. Seabirds dependent on predictable fish availability may alter breeding or migratory patterns, with cascading effects on predator-prey dynamics. Even microscopic organisms, such as phytoplankton, adjust their bloom timing and composition, subtly reshaping the foundation of the marine food web. Each of these responses is slow-moving, often imperceptible over months, but significant over decades, cumulatively altering ecosystem structure. Coastal hydrodynamics would also respond to changes in the AMOC. As water mass distribution shifts, local sea levels along the European coast can rise or fall relative to historical norms, affecting tidal patterns, estuarine flow, and the potential for storm surges. The impacts on human infrastructure are gradual yet persistent. Ports, coastal defenses, and low-lying agricultural areas would require adaptive management to accommodate slowly changing baseline conditions. Natural habitats along these coasts, salt marshes, tidal flats, and estuaries would experience altered inundation cycles, influencing breeding and feeding grounds for aquatic and avian species. These subtle environmental adjustments unfold over decades, often unnoticed until they intersect with human activity in measurable ways. Atmospheric feedbacks operate in concert with oceanic changes. A weaker AMOC modifies heat transport, which in turn influences the position and variability of the polar jet stream. Extended meanders in the jet stream can create persistent weather patterns, leading to prolonged cold spells, wet periods, or droughts across Europe. These patterns influence soil moisture, river flow, and ecosystem productivity, as well as human energy consumption and agricultural scheduling. Each seasonal cycle is subtly altered, producing shifts that accumulate over years, demonstrating the intimate coupling between ocean currents and atmospheric dynamics. Historical analogues, though imperfect, provide context for understanding potential future outcomes. During the Younger Dryas, abrupt cooling occurred over Europe and North America as ocean circulation temporarily stalled due to massive meltwater input. Average regional temperatures dropped, rivers and lakes experienced altered freeze-thaw cycles, and vegetation zones shifted accordingly. Evidence from ice cores, sediment layers, and oceanic proxies reveals rapid changes in salinity and water mass formation, reinforcing the sensitivity of the AMOC to freshwater perturbations. Modern observations suggest that contemporary changes, though less dramatic in instantaneous magnitude, follow similar principles, underscoring the relevance of past events for anticipating future climate behavior. Scientists continue to refine predictive models, incorporating complex interactions among ocean currents, atmospheric dynamics, and biogeochemical cycles. These models project multiple scenarios, ranging from moderate weakening to near collapse of the AMOC under high emission trajectories. Each scenario elucidates the potential distribution of temperature, precipitation, sea level, and ecosystem responses. While precise timing remains uncertain, the convergence of evidence from observations, historical records, and simulations indicates a consistent direction. The AMOC is sensitive to anthropogenic influences and could significantly alter European climate patterns if current trends continue. Globally, changes in the AMOC resonate far beyond the North Atlantic. Tropical precipitation systems, including the West African and South Asian monsoons, respond to shifts in heat transport and pressure patterns induced by altered ocean circulation. The Southern Ocean, Antarctic ice shelves, and associated deep water formation also experience secondary effects, propagating feedbacks that influence oceanic and atmospheric conditions worldwide. These connections exemplify the integrative role of the AMOC as a planetary scale conveyor, linking distant regions through the movement of heat, salinity, and energy. Even minor adjustments in circulation can ripple through multiple systems, illustrating the breadth of influence exerted by the movement of water across the Atlantic. Looking forward over the coming century, the trajectory of the AMOC suggests gradual yet significant transformation of climate conditions across Europe. As circulation strength diminishes, northern regions may endure longer winters punctuated by sudden cold snaps, while spring arrives later and retreats more slowly into summer. Snow accumulation patterns change, affecting river flow timing, groundwater recharge, and soil moisture. Urban heat management may be challenged as buildings contend with prolonged cold, and energy grids adjust to shifting seasonal demand. Across southern Europe, precipitation patterns may become less predictable, altering the availability of fresh water for agriculture and human consumption. Reservoirs, irrigation systems, and urban water networks would need careful management to accommodate this shifting hydrological rhythm. Ecosystems adjust in tandem with climatic changes. Forest species that once thrived under consistent winter temperatures might face slower growth or altered reproductive cycles. Tree lines in northern latitudes could descend slightly, while southern species face increased stress during hotter, drier periods. Wetlands, critical carbon sinks, respond to both water levels and freezing duration, with microbial decomposition processes adjusting to prolonged cold or fluctuating moisture. This could result in gradual carbon release into the atmosphere, subtly influencing regional and global climate patterns. Each ecological response unfolds quietly, a testament to the slow but persistent nature of environmental feedbacks. Marine life experiences parallel adjustments. Slower northward heat transport and reduced upwelling modify the distribution of plankton blooms, subtly altering the timing and abundance of primary production. Fish populations follow temperature gradients and nutrient availability, causing fisheries to adapt to shifting stock locations. Seabirds, reliant on fish and other marine prey, adjust migratory patterns and breeding schedules. Even minute changes at the base of the food web ripple outward, slowly restructuring predator-prey relationships and affecting the resilience of marine ecosystems over decades. The ocean's rhythm is slowed but still present, carrying its influence across generations. The carbon cycle remains intertwined with circulation dynamics. Deep water formation carries carbon away from surface waters, sequestering it in the ocean interior. A weakened AMOC reduces the efficiency of this process, leaving more carbon in the atmosphere and upper ocean layers, which can accelerate warming in other regions while northern Europe cools. The interplay between localized cooling and global warming illustrates the complex, non-linear consequences of disrupted circulation, emphasizing that climate responses are rarely uniform. Changes in ocean chemistry, including regional acidification, influence calcifying organisms and marine biodiversity, amplifying the cascading effects of circulation alteration. Human systems face a continuous process of adaptation. Agriculture must adjust planting schedules and crop selection in response to altered frost patterns, precipitation variability, and changing growing seasons. Energy systems accommodate higher winter demand in northern Europe, while southern regions face heat stress and water scarcity. Coastal urban planning incorporates gradually changing sea levels, modified storm surge potential, and long-term erosion risks. Infrastructure, policy frameworks, and disaster preparedness evolve incrementally, guided by the steady stream of scientific observations and projections. Even subtle variations in the AMOC can create far-reaching effects, requiring foresight and flexibility in human response. Atmospheric teleconnections extend the influence of a weakening AMOC well beyond Europe. Tropical rainfall systems, particularly monsoons in Africa and South Asia, are influenced by shifts in heat transport and surface temperatures. These changes modify regional water availability, agricultural productivity, and livelihoods for millions dependent on predictable seasonal cycles. In the Southern Hemisphere, Antarctic ice dynamics and Southern ocean circulation respond to altered heat and salinity distributions, creating feedbacks that can propagate back to the North Atlantic. The AMOC thus functions as an integrative component of the global climate system, transmitting localized changes across hemispheres through complex, interlinked processes. Paleoclimate evidence continues to inform understanding of possible outcomes. Historical events, such as abrupt cooling episodes during the last glacial period, demonstrate that relatively small changes in freshwater input and ocean circulation can produce large regional climate shifts. Ice core and sediment analyses reveal rapid salinity changes and temperature declines, reinforcing the sensitivity of the system to perturbations. Modern monitoring confirms that while the magnitude of change today may be less dramatic than in the distant past, the principles remain consistent. Perturbations in the North Atlantic have the potential to induce sustained, measurable effects across Europe and beyond. Climate models integrate these observations to project potential scenarios. Simulations consider continued ice melt, increasing greenhouse gas concentrations, and freshwater influx, generating a range of outcomes from moderate weakening to near cessation of the AMOC. Each scenario produces nuanced regional impacts affecting temperatures, precipitation, sea level, and ecosystem dynamics differently across timescales. Even within probabilistic frameworks, a consistent pattern emerges. The AMOC is highly sensitive, and its alteration will have cascading effects through climate, ecological, and human systems, reinforcing the need for careful monitoring and adaptive management strategies. The cumulative effects of these processes highlight the interconnectivity of the Earth system. Oceans, atmosphere, ecosystems, and human societies respond together to shifts in energy distribution and heat transport. A weakened AMOC produces a mosaic of outcomes: cooler winters in Europe, altered monsoon cycles, changes in marine productivity, and subtle but persistent modifications to terrestrial ecosystems. Each response is interdependent, evolving over decades, and often imperceptible in the short term, yet collectively shaping the trajectory of climate, environment, and society. Understanding these interactions requires continuous observation, rigorous modeling, and interdisciplinary collaboration, reflecting the complex elegance of planetary systems. Over longer timescales, the AMOC's weakening unfolds as a slow but pervasive influence, threading through oceans, atmosphere, and life across Europe. Decades of gradual reduction in heat transport allow regional climates to drift from established norms. In Northern Europe, prolonged cold periods could alter snowpack accumulation, soil freezing cycles, and the timing of river ice melt, subtly reshaping hydrology and influencing freshwater ecosystems. Southern Europe, conversely, may experience increasing aridity during critical growing months, stressing crops and natural vegetation alike. These shifts are not abrupt but continuous, quietly altering the rhythms of seasonal change and requiring adaptation across generations. Ecosystems respond incrementally, often with cascading effects that amplify subtle climate shifts. Forests in temperate zones experience slower tree growth and altered species composition, as some plants adapt more readily to changing frost cycles and moisture regimes than others. Wetlands and peatlands, previously stable carbon reservoirs, may see fluctuating water levels that influence both plant communities and microbial decomposition rates. Extended freezing or irregular thawing affects nutrient availability, indirectly modifying productivity and carbon sequestration potential. Over decades, these ecological adjustments cumulatively reshape landscapes, creating conditions that differ significantly from those observed in historical climate records. Marine systems reveal analogous patterns of slow but meaningful change. The reduction of nutrient upwelling associated with a weakened AMOC shifts the timing and location of phytoplankton blooms. Fish and invertebrate species respond by migrating to areas with more favorable conditions, altering predator-prey relationships and the structure of the marine food web. Seabirds and marine mammals reliant on consistent prey availability adjust reproductive and migratory behaviors. These modifications, while subtle in any single year, accumulate over time, slowly restructuring marine communities and affecting the human economies that depend on them. Carbon storage dynamics further illustrate the systemic consequences of AMOC weakening. Deep water formation, responsible for sequestering atmospheric carbon into the ocean interior, becomes less efficient as circulation slows. Consequently, more carbon remains in surface waters and the atmosphere, contributing to regional and global warming in areas outside Europe. The duality of cooler northern Europe and broader warming elsewhere exemplifies the non-linear, spatially heterogeneous responses of the climate system to a single oceanic alteration. The interplay between circulation, carbon flux, and surface temperatures demonstrates the intricate feedbacks that govern planetary climate stability. Human societies, deeply integrated with these environmental systems, must contend with gradual but persistent changes. Agricultural cycles require ongoing adjustments to planting schedules, crop varieties, and irrigation practices in response to altered precipitation and frost timing. Energy infrastructure faces increased winter demand in northern latitudes and stress from warmer summers in southern regions. Coastal communities contend with slowly rising sea levels and modified storm surge patterns, necessitating incremental adaptation in urban planning, infrastructure reinforcement, and emergency preparedness. Societal resilience is continuously tested by the quiet, persistent influence of an altered ocean circulation system. Atmospheric responses to AMOC weakening extend the influence globally. Shifts in North Atlantic heat distribution alter the positioning and intensity of the polar jet stream, influencing weather patterns across Europe and North America. Teleconnections impact tropical rainfall systems, modulating the timing and intensity of monsoons in Africa and South Asia, while Southern Hemisphere, oceanic and ice dynamics adjust to modified heat and salinity distributions. These interactions illustrate that changes in one component of the climate system reverberate through the entire global network, highlighting the AMOC's integrative role as a planetary-scale engine of energy and mass redistribution. Historical analogues provide crucial perspective on these processes. Rapid cooling events during the last glacial period, particularly the Younger Dryas, demonstrate that even modest perturbations in freshwater input can induce abrupt regional climate shifts. Ice cores, sediment records, and ocean proxies reveal sudden changes in salinity and temperature, corroborating the sensitivity of overturning circulation to external forcing. Contemporary observations suggest that while the current rate of change is slower than in these historical events, the underlying mechanisms remain consistent, underscoring the relevance of paleoclimate studies for understanding modern climate risks. Model projections further elucidate the range of potential outcomes. Simulations incorporating ice melt, greenhouse gas concentrations, and freshwater influx predict scenarios ranging from moderate weakening to near cessation of the AMOC. Even partial reductions produce measurable effects on temperature, precipitation, sea level, and ecosystems across Europe and globally. The integration of observational data with these models enables scientists to anticipate changes and inform adaptation strategies, though inherent uncertainties in timing and magnitude remain. The convergence of multiple lines of evidence affirms that the AMOC is highly sensitive, and its alteration carries widespread implications for both natural and human systems. The continuous and interdependent nature of these processes reinforces the subtlety of long-term change. Oceans, atmosphere, terrestrial ecosystems, and human societies respond in tandem, with impacts accumulating slowly yet persistently. The weakening of the AMOC does not manifest as a single dramatic event, but as a series of small, interlinked shifts that collectively reshape climate patterns, ecological dynamics, and societal conditions. Observing and understanding these transformations requires careful, sustained measurement and analysis, capturing the gradual evolution of an intricate system that governs regional and global climates. As decades progress into a full century, the persistent influence of a weakened AMOC continues to shape both natural and human systems. Northern European winters, prolonged and intensified, alter snow accumulation and soil freeze-thaw cycles, affecting hydrological systems, river flow timing, and wetland dynamics. Gradual shifts in river discharge influence nutrient transport to coastal areas, subtly modifying estuarine and nearshore marine ecosystems. Southern regions face increasingly erratic rainfall patterns, challenging water management infrastructure and intensifying competition for fresh water among agriculture, urban supply, and natural habitats. Even incremental changes in the timing or quantity of precipitation ripple outward, influencing soil fertility, crop productivity, and the resilience of natural vegetation. Forests across temperate and boreal regions respond to these slow climatic shifts with nuanced alterations. Species composition gradually adapts, with frost-sensitive trees retreating in favor of hardier varieties, while soil microbial activity adjusts to the extended periods of cold and variable moisture. The long-term trajectory of peatlands and wetlands is influenced by subtle alterations in hydrology, with decomposition rates and carbon storage modulated by the interplay of freezing, thawing, and water saturation. Over decades, these ecosystems recalibrate, preserving function but transforming in structure, illustrating the quiet yet persistent influence of oceanic changes on terrestrial habitats. Marine ecosystems continue to adjust in response to slower circulation. Variations in upwelling and nutrient transport subtly shift the timing and productivity of phytoplankton blooms, with cascading effects throughout food webs. Fish and invertebrate species follow thermal and nutrient gradients, causing incremental shifts in distributions that affect both predator-prey dynamics and human fisheries. Seabirds and marine mammals modify migratory routes and breeding patterns in response to these changes, reflecting the interdependence of oceanic and atmospheric processes. Each alteration is gradual, often imperceptible year to year, yet collectively these shifts reshape ecosystem structure over long temporal scales. Carbon dynamics illustrate the interconnectedness of oceanic and atmospheric processes. Reduced deepwater formation slows the transport of carbon from surface waters to the ocean interior, leaving more CO2 available in the atmosphere. The resulting regional cooling in Northern Europe occurs concurrently with warming in other regions, demonstrating the non-uniform, spatially heterogeneous consequences of circulation changes. Ocean acidification may accelerate in areas of reduced circulation, affecting calcifying organisms and modifying marine biogeochemical cycles. These shifts, while gradual, persist over decades, influencing the climate system, oceanic chemistry, and the productivity of ecosystems. Societal systems evolve alongside these environmental changes. Agriculture adjusts planting cycles and crop selection in response to altered frost dates and precipitation variability. Energy systems in northern latitudes adapt to increased winter demand, while southern regions contend with heat stress and water scarcity. Coastal cities, informed by slowly rising sea levels and modified storm surges, implement adaptive infrastructure, shoreline defenses, and long-term planning measures. Transportation, urban services, and emergency management all experience incremental pressures as climate conditions slowly drift from historical norms, illustrating the persistent, far-reaching consequences of oceanic circulation changes. Atmospheric teleconnections continue to transmit the effects of AMOC weakening across the globe. Shifts in North Atlantic heat transport influence jet stream patterns, affecting weather variability in Europe, North America, and beyond. Monsoon systems in Africa and South Asia respond to altered temperature and pressure distributions, modifying rainfall timing and intensity. In the Southern Hemisphere, Antarctic ice shelves and the Southern Ocean adjust to redistributed heat and salinity, generating feedbacks that can propagate back to the North Atlantic. The AMOC thus functions as a planetary integrator, connecting distant regions through energy, mass, and momentum transfer, highlighting the global significance of localized oceanic changes. Paleoclimate analogues continue to provide insight into long-term responses. Historical episodes, such as abrupt cooling during the last glacial period, demonstrate that minor perturbations in freshwater input can trigger rapid regional climate shifts. Ice core and sedimentary evidence show sudden changes in salinity, temperature, and deep water formation rates, reinforcing the sensitivity of overturning circulation to small disturbances. Modern observations, though more gradual, follow similar principles, highlighting the relevance of past events for anticipating future outcomes and understanding thresholds within the climate system. Modeling studies project a spectrum of potential long-term scenarios. Simulations incorporating ongoing ice melt, greenhouse gas emissions, and freshwater influx suggest varying degrees of AMOC weakening, each with regionally distinct impacts on temperature, precipitation, sea level, and ecosystem productivity. Even partial reductions in circulation produce measurable consequences, reinforcing the importance of sustained observation, interdisciplinary research, and adaptive management. The integration of empirical data with predictive models allows scientists to explore potential trajectories, anticipate challenges, and develop mitigation strategies for ecological, societal, and economic systems influenced by oceanic circulation changes. The cumulative impact of a weakened AMOC over multiple decades illustrates the subtlety and persistence of climate feedbacks. Oceans, atmosphere, terrestrial ecosystems, and human systems respond collectively to changes in heat and mass distribution, producing gradual yet far-reaching transformations. Cooler winters in northern Europe, altered monsoon patterns, marine ecosystem restructuring, and incremental shifts in terrestrial vegetation illustrate the interconnected nature of these processes. Understanding and responding to these transformations requires continuous observation, scientific analysis, and a long-term perspective, reflecting the quiet but powerful influence of one of Earth's largest and most intricate climate regulators. As the timescale extends into multiple centuries, the influence of a weakened AMOC becomes ever more integrated into the rhythms of Earth's systems. Ocean circulation, though slowing incrementally, exerts continuous control over the distribution of heat and salinity, guiding patterns of climate and influencing the persistence of seasonal cycles. Northern Europe may experience prolonged periods of reduced temperatures during winter months, with snowpack and soil freezing affecting rivers, wetlands, and groundwater recharge. Vegetation cycles adjust accordingly, with delayed leaf emergence in forests and shifts in flowering phenology, gradually altering ecosystem structure and function over generations. Southern Europe, conversely, faces persistent challenges associated with shifts in rainfall and drought frequency. Croplands, forests, and grasslands adapt slowly to modified water availability, impacting both productivity and biodiversity. Agricultural systems must continuously adjust to subtle changes in frost occurrence, precipitation timing, and soil moisture, while hydrological networks attempt to accommodate fluctuating river flows and reservoir levels. The cumulative impact of these shifts subtly reshapes landscapes, creating conditions that, though not immediately apparent year to year, differ markedly from those experienced in previous centuries. Marine ecosystems are equally affected by long-term circulation changes. Reduced nutrient upwelling modifies the timing and spatial distribution of primary production, influencing plankton blooms that underpin entire food webs. Fish populations migrate toward optimal conditions, altering local predator-prey interactions and reshaping fisheries productivity. Seabirds and marine mammals adjust migratory and breeding behaviors to follow these changes, demonstrating the integrated response of biological systems to subtle oceanic variation. Over centuries, these adjustments result in restructured ecosystems with new balances and community compositions emerging across both coastal and open ocean environments. The carbon cycle remains closely tied to circulation dynamics. A slower AMOC reduces the vertical transport of carbon into the ocean interior, leaving more CO2 in surface waters and the atmosphere. While northern Europe may cool under these conditions, global warming elsewhere continues, highlighting the heterogeneous spatial response of the climate system. Ocean acidification, already affecting sensitive calcifying species, may intensify regionally due to altered circulation, influencing biodiversity and biogeochemical cycling over long timescales. These subtle, persistent interactions between carbon transport, ocean chemistry, and climate reinforce the interconnected nature of planetary systems. Human societies evolve within this slowly transforming environmental framework. Infrastructure, agriculture, and energy systems respond incrementally to changes in climate and hydrology. Northern regions require sustained adaptation to extended winters and shifting precipitation patterns, while southern regions contend with water scarcity and increased heat stress. Coastal areas monitor sea level trends and storm surge potential, adapting port operations, flood defenses, and urban planning accordingly. Societal resilience is exercised continuously, informed by long-term observation, modeling, and iterative management strategies, emphasizing the gradual, persistent impact of ocean circulation on daily life and future planning. Atmospheric teleconnections continue to transmit the consequences of AMOC weakening globally. Shifts in North Atlantic heat and salinity alter the position and variability of the jet stream, affecting weather patterns across Europe, North America, and parts of Asia. Monsoon systems respond to these changes, modifying rainfall timing and intensity in Africa and South Asia, while Southern Hemisphere oceans adjust to redistributed heat and salinity, creating feedbacks that influence global climate patterns. The AMOC thus functions as a planetary integrator, connecting distant regions through a subtle but persistent movement of energy and mass, demonstrating the systemic reach of changes in a single ocean current. Paleoclimate evidence reinforces the lessons of potential long-term impacts. Rapid cooling events during the last glacial period demonstrate that relatively minor perturbations in freshwater input can trigger significant regional climate shifts. Ice cores, sediment layers, and ocean proxies reveal abrupt changes in salinity, temperature, and deep water formation, illustrating the sensitivity of the AMOC to external forcing. Contemporary observations, although occurring on a slower timescale, suggest that the principles governing past events remain relevant, providing a context for understanding the potential magnitude and persistence of future transformations. Model projections, integrating centuries of potential environmental change, illustrate a spectrum of plausible scenarios: continued ice melt, Rising greenhouse gas concentrations and freshwater influx may reduce the strength of the AMOC partially, or, in extreme cases, near cessation. Even partial weakening produces measurable, long-term effects on regional and global temperatures, precipitation, sea level, and ecosystem productivity. Coupled climate models, informed by observational datasets, allow researchers to anticipate these outcomes, explore thresholds, and guide long-term adaptation strategies across natural and human systems. The convergence of evidence from multiple sources underscores the critical role of the AMOC in regulating climate and ecosystem stability. Over the span of centuries, the cumulative effects of these processes manifest in subtle but enduring transformations. Northern Europeans' landscapes adjust to prolonged cold, altered snow and river cycles, and shifting vegetation patterns. Southern regions experience persistent modifications to hydrology, agriculture, and ecosystem structure. Marine food webs reorganize gradually as nutrient availability and temperature profiles evolve. Carbon transport and storage patterns adapt to slower circulation, influencing atmospheric composition and climate feedbacks on regional and global scales. Human societies continuously interpret and respond to these changes, shaping infrastructure, resource management, and policy over generations. The slow rhythm of change, imperceptible in a single season but evident across decades and centuries, defines the profound, persistent impact of the AMOC on life across the Northern Hemisphere and beyond. Over successive centuries, feedback mechanisms within the climate system begin to accentuate the influence of a weakened AMOC. As Northern Europe remains cooler for extended periods, soil and vegetation dynamics shift in tandem. Prolonged freezing slows the decomposition of organic material in forests and wetlands, slightly altering nutrient cycling and carbon release rates. These changes in turn influence local atmospheric composition, subtly modifying humidity and temperature patterns. Rivers, lakes, and groundwater respond to the slow drift in snowmelt timing and rainfall distribution, affecting aquatic habitats and the species that rely on them. Each adjustment is incremental, yet over multiple generations, the cumulative effect creates conditions distinct from those experienced in prior centuries. Coastal environments, sensitive to both hydrological and oceanic change, evolve gradually under these conditions. Shifts in tidal amplitude and storm surge frequency, driven by variations in sea level and the redistribution of ocean mass, influence sediment transport and shoreline morphology. Estuarine and tidal ecosystems respond to altered salinity and inundation patterns, affecting breeding grounds for fish, crustaceans, and migratory birds. Human settlements along these coasts adjust slowly, reinforcing infrastructure, modifying land use, and refining disaster preparedness strategies. The interplay of subtle natural and human adaptation illustrates the persistent, almost imperceptible reach of circulation changes over long timescales. Marine food webs continue their slow adaptation. Phytoplankton, influenced by changes in nutrient availability and temperature, bloom at different times and in new areas, influencing zooplankton populations and the fish species that feed upon them. Predatory fish and marine mammals follow these shifts, gradually redistributing themselves across oceanic regions to optimize energy intake and reproductive success. These adjustments are not abrupt, yet they produce measurable effects over decades and centuries, reshaping community structures and ecosystem dynamics. Even the smallest organisms, from plankton to benthic invertebrates, participate in this slow ecological restructuring, reflecting the interconnected nature of ocean circulation and life. The global carbon cycle continues to reflect the consequences of slow deep water formation. Reduced sequestration of atmospheric carbon into the ocean interior allows CO2 concentrations to persist in the upper ocean and atmosphere, amplifying warming in regions outside northern Europe. Simultaneously, regional cooling in Europe may reduce the length of the growing season for plants, slightly affecting photosynthetic carbon uptake. Ocean acidification persists in areas of slow circulation, impacting calcifying species and altering marine biogeochemistry over centuries. These interlinked processes exemplify the non-linear, spatially heterogeneous nature of climate responses to oceanic shifts, illustrating that a single current's modulation reverberates throughout the biosphere. Human societies, intertwined with these environmental transformations, continue a steady process of adaptation. Agricultural strategies evolve incrementally, informed by observations of frost occurrence, precipitation variability, and soil moisture trends. Energy infrastructure in northern regions adjusts to increased winter demand and prolonged cold, while southern regions contend with warming stress and intermittent water scarcity. Urban planning along coasts incorporates long-term projections of sea level rise and changing storm surge probabilities, resulting in gradually modified flood defenses, port management, and land use. Societal resilience is exercised continuously, guided by the slow, cumulative signals emitted by both human and natural systems as they respond to ongoing changes in oceanic circulation. Atmospheric teleconnections maintain their influence across hemispheres. The weakening of the AMOC modifies the distribution of heat and pressure in the North Atlantic, influencing the jet stream and altering weather patterns across Europe and North America. Monsoon systems respond to changes in oceanic heat distribution, impacting rainfall and agricultural timing in Africa and South Asia. Southern Hemisphere oceans adjust to redistributed heat and salinity, generating feedbacks that return to the North Atlantic and contribute to complex global climate dynamics. The AMOC operates as a planetary integrator, continuously linking distant regions through subtle but persistent movements of heat, mass, and momentum. Paleoclimate records continue to serve as reference points for long-term understanding. Historical abrupt cooling events illustrate the sensitivity of overturning circulation to relatively modest freshwater inputs. Ice cores, sedimentary layers, and oceanic proxies reveal rapid shifts in salinity and temperature, highlighting the potential for sustained regional climate change. Contemporary observations, occurring more gradually, confirm that the mechanisms remain relevant, emphasizing the importance of continuous monitoring and interdisciplinary analysis. By comparing past and present, scientists can identify thresholds, anticipate systemic responses, and refine projections for both environmental and societal planning. Climate models projecting multi-century outcomes depict a spectrum of potential changes, incorporating ongoing ice melt, greenhouse gas accumulation, and freshwater influx. Simulations explore the range from moderate weakening to near cessation of the AMOC. Partial reductions already produce measurable effects on temperature, precipitation, ecosystem structure, and sea level, while more severe scenarios amplify these impacts globally. By integrating empirical observations With model outputs, researchers can anticipate long-term environmental shifts, guide adaptation measures, and identify potential tipping points, highlighting the central role of the AMOC in shaping climate, ecosystems, and human societies over centuries. Through the slow unfolding of these processes, the cumulative consequences become clear. Northern Europe gradually adjusts to prolonged cold and altered seasonal cycles. Southern regions face persistent variability in water availability, and marine ecosystems restructure in response to nutrient and temperature changes. Carbon transport and storage patterns evolve with circulation shifts, affecting atmospheric composition and climate feedbacks. Human societies respond incrementally, adapting agriculture, energy use, and urban infrastructure to changing conditions. Over centuries, the quiet but persistent influence of the AMOC manifests in broad, interlinked transformations that define the trajectory of both natural and human systems. As centuries advance, the slow transformation of Earth systems under a weakened AMOC continues to unfold with quiet persistence. Northern Europe experiences extended winters punctuated by variable snow cover, shaping river hydrology and groundwater levels. Lakes and wetlands adapt to prolonged ice cover and shifting inflows, influencing aquatic habitats and the timing of breeding for amphibians, fish, and waterfowl. Soil moisture patterns evolve gradually, affecting plant communities, nutrient cycling, and forest productivity. Even minor variations in seasonal cycles, repeated across decades, accumulate into discernible changes in ecosystem composition and function. Southern Europe faces long-term adjustments in water availability and climate patterns. Rainfall variability influences agricultural yields, forest health, and natural vegetation resilience. Irrigation systems contend with uneven river flow and prolonged dry periods, while drought-sensitive species adjust distribution ranges or experience gradual population declines. Across this region, human societies engage in continuous adaptation, refining water management strategies, crop selection, and energy use. The slow accumulation of climate effects subtly reshapes daily life, governance, and resource planning, without abrupt transitions but with persistent, tangible consequences over generations. Marine environments reflect a parallel evolution. Reduced circulation shifts nutrient delivery and alters temperature profiles, changing the timing and spatial distribution of primary productivity. Fish populations follow these gradients, slowly redistributing themselves, which cascades through predator-prey dynamics and impacts human fisheries. Seabirds and marine mammals respond by modifying breeding sites and migratory timing, while benthic communities adjust to subtle changes in sedimentation and nutrient deposition. Over centuries, these incremental shifts collectively restructure marine ecosystems, illustrating the interconnectedness of circulation, biological productivity, and human dependence on ocean resources. The global carbon cycle responds in tandem. Reduced deep water formation limits the sequestration of carbon, leaving more CO2 in surface waters and the atmosphere. While Northern Europe experiences regional cooling, other areas continue to warm, demonstrating the heterogeneous nature of climate response. Ocean acidification persists in areas of slow circulation, influencing calcifying species and marine biogeochemistry. Terrestrial ecosystems contribute their own slow feedbacks. Shifts in vegetation growth, decomposition, and carbon storage modulate local and regional atmospheric composition. The combined effect of oceanic and terrestrial processes generates a persistent, multi-scale modulation of the climate system. Human infrastructure and societal systems operate within this evolving framework. Agriculture adjusts incrementally to changes in frost timing, precipitation patterns, and soil moisture, while energy systems respond to prolonged winter heating needs and summer variability. Coastal settlements account for slowly rising sea levels and changing storm surge probabilities, reinforcing protective infrastructure, modifying port operations, and adapting land use planning. Transportation, urban services, and resource distribution systems evolve subtly over generations, guided by long-term climate observation and planning. Each adaptation is measured, gradual, and continuous, reflecting the persistent, ongoing influence of altered ocean circulation on human life. Atmospheric teleconnections propagate these changes across distant regions. The redistribution of heat and salinity in the North Atlantic modifies the jet stream, altering the frequency, intensity, and persistence of weather systems across Europe, North America, and Asia. Monsoon systems in Africa and South Asia adjust to altered oceanic heat transport, influencing rainfall timing, intensity, and ecosystem productivity. Southern Hemisphere oceans respond to redistributed heat and salinity, generating feedbacks that reverberate back to the North Atlantic. These global linkages underscore the AMOC's role as a planetary integrator, continuously connecting disparate regions through subtle flows of energy and mass. Paleoclimate evidence continues to illuminate the sensitivity of ocean circulation. Abrupt cooling events during the last glacial period demonstrate that small freshwater inputs can produce rapid regional climate shifts. Ice cores, sedimentary layers, and oceanic proxies reveal changes in salinity, temperature, and deep water formation, emphasizing the responsiveness of overturning circulation to perturbation. Present-day observations, while slower in pace, reflect the same underlying mechanisms. Studying past events alongside contemporary data allows scientists to identify thresholds, anticipate systemic responses, and refine models for both environmental and societal planning. Modeling studies, extending across centuries, project a range of scenarios under continued ice melt, greenhouse gas accumulation, and freshwater influx. Even moderate weakening of the AMOC produces measurable impacts on temperature, precipitation, sea level, and ecosystem productivity. More severe reductions amplify these effects, producing substantial regional differences and cascading global consequences. Integrated modeling, informed by empirical observation, enables the anticipation of long-term changes, the identification of potential tipping points, and the development of adaptation strategies. The persistent influence of the AMOC thus emerges as a critical determinant of planetary climate stability. Over these extended timescales, the cumulative effect of a weakened AMOC becomes evident in the interwoven transformations of climate, ecosystems, and human systems. Northern Europe gradually adapts to longer winters, altered snow and river cycles, and shifting vegetation patterns, while southern regions contend with persistent hydrological variability and ecological stress. Marine ecosystems restructure incrementally as nutrient and temperature profiles shift, and carbon transport evolves alongside circulation changes, influencing atmospheric composition and global climate feedbacks. Human societies, continually interpreting subtle environmental signals, adapt infrastructure, agricultural practices, and water management in response. The slow, persistent rhythm of these changes defines the influence of the AMOC across centuries, a reminder of the intricate and interconnected dynamics that sustain planetary equilibrium. As the timeline stretches further, beyond several centuries, the persistent influence of a weakened AMOC manifests in increasingly intricate ways. Northern Europe, subjected to prolonged cold spells and extended periods of snow and ice cover, sees subtle but cumulative modifications to hydrological cycles. Rivers maintain altered flow regimes, with delayed spring meltwater influencing nutrient transport and the timing of aquatic ecosystems. Wetlands and floodplains, adapting to shifts in inundation and freezing patterns, gradually modify their vegetative and microbial communities, influencing carbon cycling on a regional scale. These incremental adjustments, almost imperceptible year to year, accumulate over generations, subtly reshaping both terrestrial and freshwater ecosystems. Southern Europe experiences long-term alterations in precipitation distribution and intensity. Extended drought periods interspersed with episodic heavy rainfall events influence soil fertility, water availability, and vegetation dynamics. Agricultural systems must adapt through crop selection, irrigation scheduling, and long-term soil management, while natural ecosystems respond through shifts in species composition, reproductive timing, and interspecific interactions. Even minor, persistent hydrological changes propagate through landscapes, gradually reshaping ecological niches and the services they provide to human populations. The slow pace of these transformations does not diminish their significance, for the accumulation of subtle changes defines centuries of environmental evolution. Marine environments reflect continuous adjustment to altered circulation, reduced nutrient transport, and shifts in thermal gradients reshape the timing and location of phytoplankton blooms, cascading through food webs and influencing fish, invertebrate, and apex predator populations. Seabird colonies and marine mammals adjust breeding and migratory behavior in response to the evolving availability of prey. Benthic communities respond to gradual changes in sedimentation and oxygenation, slowly altering the structure and function of seafloor ecosystems. Over the centuries, these incremental modifications redefine marine productivity, ecosystem interactions, and the distribution of species, demonstrating the systemic integration of ocean circulation and life. The carbon cycle remains tightly coupled to circulation dynamics. Slower deep water formation reduces the sequestration of atmospheric carbon, leaving more CO2 in surface waters and the atmosphere. Northern Europe may experience regional cooling, yet global warming intensifies elsewhere, illustrating the heterogeneous response of the climate system. Ocean acidification continues to progress in areas of diminished circulation, affecting calcifying organisms and modifying marine biogeochemical cycles. Terrestrial ecosystems contribute incremental feedbacks. Slower plant growth and altered decomposition under extended winter conditions subtly influence atmospheric carbon levels. These multi-layered interactions emphasize the intricate connectivity between ocean dynamics, biogeochemistry, and climate. Human societies continue to navigate the cumulative consequences of these environmental shifts. Agriculture requires ongoing adjustments in planting schedules, crop choice, and water management, responding to evolving frost dates, precipitation patterns, and soil moisture conditions. Energy systems in northern regions adapt to extended heating needs, while southern regions address increased summer temperatures and intermittent droughts. Coastal communities integrate long-term projections of sea level change and modified storm surge probability into infrastructure planning and urban management. Across generations, these adaptations occur quietly, guided by careful observation and iterative management, reflecting the subtle, persistent influence of ocean circulation on human systems. Atmospheric teleconnections persist in transmitting the impact of AMOC weakening globally. Alterations in North Atlantic heat and salinity distributions influence the polar jet stream, shifting weather patterns across Europe, North America, and parts of Asia. Monsoonal systems in Africa and South Asia adjust in response to these changes, with rainfall timing and intensity affecting ecosystems, agriculture, and human livelihoods. Southern Hemisphere oceans respond to redistributed heat and salinity, generating feedbacks that reverberate back to the North Atlantic. The AMOC operates as a planetary integrator, linking distant regions through slow, continuous flows of energy, mass, and momentum, demonstrating the extensive reach of changes in a single oceanic current. Paleoclimate evidence underscores the sensitivity and persistence of these processes. Past abrupt cooling events, including those during the last glacial period, reveal how minor freshwater inputs can trigger substantial regional climate shifts. Ice cores, sediments, and oceanic proxies document rapid changes in salinity, temperature, and deep water formation rates, providing a context for contemporary observations. Modern measurements, while capturing slower trends, reflect the same fundamental dynamics, emphasizing the importance of continuous monitoring, interdisciplinary research, and the long-term perspective necessary to anticipate and understand the enduring consequences of altered circulation. Model projections extending over centuries depict a continuum of potential outcomes. Gradual ice melt, rising greenhouse gas levels, and persistent freshwater influx produce scenarios ranging from moderate AMOC weakening to near cessation. Even partial reductions yield measurable changes in temperature, precipitation, sea level, and ecosystem productivity, while more severe weakening amplifies these effects globally. Coupled models, informed by empirical observation, allow for exploration of thresholds, identification of potential tipping points, and development of adaptive strategies across natural and human systems. Over centuries, the persistent, quiet influence of the AMOC becomes evident in the cumulative reshaping of climate, ecosystems, and societal adaptation. Ultimately, the slow and continuous modulation of Earth systems by a weakened AMOC illustrates the subtle power of ocean circulation. Northern Europe adjusts to longer winters, altered hydrology, and shifting ecosystems, while southern regions face persistent variability and ecological adaptation. Marine ecosystems restructure incrementally, carbon dynamics evolve, and atmospheric patterns convey changes across continents. Human societies, guided by observation and responsive planning, adapt to long-term environmental trends. Over centuries, the quiet rhythm of these processes defines a trajectory of gradual transformation, demonstrating the intricate interdependence of ocean currents, climate, ecosystems, and human activity. In the final centuries of AMOC weakening, the interconnectedness of climate, ecosystems, and human societies becomes increasingly evident. Northern Europe, subjected to sustained regional cooling, experiences consistent alterations in snow cover, soil freezing, and hydrological cycles. Forests adjust their growth patterns, with some species retreating and others thriving under prolonged cold, subtly shifting biodiversity and forest structure. Wetlands and peatlands, responding to altered inundation and freeze-thaw regimes, slowly change carbon storage dynamics, influencing local atmospheric composition over extended timescales. Rivers maintain modified flow patterns, affecting nutrient transport, sediment deposition, and aquatic habitats, gradually redefining freshwater ecosystems. Southern Europe faces persistent climatic variability, with droughts and episodic heavy rainfall shaping both natural and managed landscapes. Agriculture relies on continuous adaptation, adjusting crop varieties, planting schedules, and water management practices to accommodate shifting precipitation and soil moisture patterns. Natural ecosystems respond in turn, altering species distributions, reproductive timing, and interspecific interactions. These cumulative, long-term adjustments create landscapes and ecological dynamics markedly different from historical conditions, demonstrating the quiet but enduring influence of altered ocean circulation. Marine systems continue their gradual restructuring. The reduction in nutrient transport and subtle shifts in thermal gradients influence phytoplankton productivity, which cascades through zooplankton, fish, and apex predators. Fish populations redistribute gradually, modifying predator-prey interactions and influencing human fisheries. Seabirds and marine mammals adjust breeding and migratory behaviors to follow these evolving food resources. Over centuries, these shifts establish new ecological equilibriums in both coastal and open ocean environments, reflecting the persistent integration of ocean circulation with life across trophic levels. The carbon cycle, tightly coupled with circulation, reflects ongoing long-term consequences. Slower deep water formation limits the sequestration of atmospheric carbon, leaving CO2 in surface waters and the atmosphere, contributing to regional cooling in Northern Europe and warming elsewhere. Ocean acidification progresses incrementally in areas of slowed circulation, affecting calcifying organisms and marine biogeochemistry. Terrestrial ecosystems respond slowly to changing seasonal patterns, modifying plant growth and decomposition cycles, which subtly influence carbon fluxes. These multi-layered interactions illustrate the non-linear and spatially heterogeneous consequences of a weakened AMOC. Human societies continue to adapt steadily. Agricultural systems, informed by persistent observation of frost dates, rainfall patterns, and soil conditions, adjust planting schedules and crop selection. Energy infrastructure accommodates longer winter demand and summer variability. Coastal cities reinforce defenses and modify land use to respond to long-term sea level trends and changing storm surges. Across generations, these adaptations accumulate, reflecting the ongoing, measured influence of a changing ocean on human activity and planning. Atmospheric teleconnections persist in transmitting the AMOC's influence globally. Heat and salinity redistribution modifies the jet stream, affecting European, North American, and Asian weather patterns. Monsoon systems in Africa and South Asia adjust to these shifts, influencing rainfall, ecosystems, and human livelihoods. Southern Hemisphere oceans respond to redistributed heat and salinity, generating feedbacks that reverberate back to the North Atlantic. The AMOC functions as a planetary integrator, linking distant regions through slow, continuous flows of energy and mass, illustrating the global scale of consequences arising from a single oceanic system. Paleoclimate analogues, when combined with long-term observations and modeling, provide perspective on the potential persistence and magnitude of these changes. Historical abrupt cooling events, such as those during the last glacial period, demonstrate that small freshwater inputs can provoke substantial regional climate shifts. Modern observations, though occurring more gradually, confirm similar sensitivities in the AMOC, emphasizing the importance of sustained monitoring, modeling, and adaptation planning. By integrating past and present data, scientists can anticipate thresholds, understand feedback mechanisms, and develop strategies to manage both natural and societal systems over centuries. Model projections depict a spectrum of long-term scenarios under continued ice melt, greenhouse gas accumulation, and freshwater influx. Even partial weakening of the AMOC produces measurable impacts on climate, ecosystems, and human systems, while more severe reductions amplify these effects globally. By examining these simulations, researchers gain insight into potential thresholds, feedbacks, and cascading consequences. The cumulative, multi-century influence of a weakened AMOC becomes evident, shaping regional climates, ecosystems, and human societies in subtle, interconnected ways. In reflection, the AMOC's gradual weakening reminds us of the intricate interdependence of Earth's systems. Northern Europe adapts to longer winters, altered hydrology, and shifting ecosystems, while southern regions contend with persistent variability and ecological stress. Marine environments restructure gradually, carbon dynamics evolve, and atmospheric changes ripple across continents. Human societies, guided by observation, planning, and incremental adaptation, adjust to the long-term signals of these environmental transformations. Across centuries, the slow, persistent rhythm of change leaves a quiet but undeniable imprint, illustrating the profound and interconnected influence of a single ocean current on life across the planet.